So let's start the penultimate set of slides. So let's go to full screen. Okay, so this second part on data is about wrangling, right? So how to manipulate data once we've read it in using what we went through in the last set of slides. So before we sort of get onto wrangling, I think it's important just to quickly go through the tidyverse, something that we mentioned a few times with the packages. So when it comes to data wrangling, this sort of a new approach came about maybe in the last 5 or 6 years in R, has been developed out of these tidyverse set of packages. And that's because in sort of base R, these sort of original R packages, some of the functions, especially for manipulating data, can be really difficult to sort of understand, and can be quite slow when you're dealing with big data sets. And so there's been a few attempts, a few different packages that have tried to make handling data easier in R. And this is why I'm going through the tidyverse rather than some of the other functions, because I think they can be a bit better. So yeah, previously we would use stuff like functions like subset or with, merge, transform, split, reshape, and they are really quite painful to learn and to understand. They all have like different argument names and different orders of the arguments, and they don't really flow that well together when you're creating data frames. And something like reshape, I never. It was kind of like the function you would use every few weeks, but you could never remember exactly how to do it. You would have to look at the help file every time, and the help file was not so easy to really understand. Okay, so the tidyverse collections as sort of a nice way of handling data, better than these sort of base R data. And the idea behind this tidyverse is that there's some sort of common philosophy for data and programming, and that we can sort of they sort of created the functions to work together. And these have been sort of created by Hadley Wickham again at RStudio and his colleagues there. So yeah, what they see at least is that when you come to R and you have sort of a data analysis workflow, that you sort of go through these steps where you import the data and then you tidy the data, which is what we'll talk about next. Then you might transform the data, which we'll talk about towards the end of these slides. Then you might want to visualize it, like using ggplot. You might want to model it, and maybe you go around in a circle a bit until you really can understand your data set. And then finally, you might want to communicate the results. So in each of these sort of steps, you sort of develop packages that can help for each of these. We're really going to focus on these two in these part of the slides, having already gone through visualize and import before. Okay, so when we load tidyverse, you might have seen this when I did it in R. It loads 8 packages. Yeah, so these are the 8 packages, and some of them we talked about already. ggplot2. We talked about tibbles, which are within the tibble package. We talked a little bit later about dplyr and tidyr. And readr we talked about, and forcats, and stringr for working with character strings. Okay, so again, this is what we see when we load load tidyverse. Sorry, that we see that different the 8 packages are being loaded. And this is just saying that for these 2 functions, there's a bit of a conflict, right? There's 2 filter functions, and so by default we'll be using the dplyr version. So it's higher up in that global environment that I talked about in the second set of slides. So when we install the tidyverse, it actually installs more than these 8 packages. I think it installs maybe 30 odd packages, including like readxl and some of these other packages. So when we load tidyverse, it loads like these sort of 8 kind of core packages that you're likely to use quite often, and then the ones like readxl that perhaps you're less likely to use, you have to load separately. Okay, so the idea behind the tidyverse is that there's really an optimal way to organize data frames. So we can we see data frames organized many different ways. Just like visit national statistics offices, then each data frame and each organization might arrange the data differently. But in R, we tend to like data arranged in a specific way, this sort of tidy way. And in this case, what we really like is when variables have their own column in the data frame. So by that we mean if it's a variable and we just want sort of one single column for all the data that's from the same variable, and not variable sort of spread over multiple columns. And then for each observation, we sort of want a row for each observation, and then values are sort of what we call the inside of the cell that contains the value. So this is what they sort of termed tidy data. And what is true for R is also true for most other statistical programming languages, that they're sort of vectorized programming languages. So that means they really like variables in vectors, in columns, and a lot of the machinery sort of behind R and other programming, other statistical languages sort of optimized to work with vectors. So it's always sort of good to have this idea of when you're reading in data from the wild that you can have the tools to sort of tidy the data to get it into this sort of common format, because it's going to make data manipulations a lot quicker, and you'll be able to apply a lot more functions to it. So yeah, unfortunately, like when we go to national statistics offices or survey sort of websites, it's rare that the data is in exactly the format that R would like and that it will work perfectly with. So tidying the data can sometimes, depending on the format, can take a lot of time, and so sort of learning the functions behind how to manipulate the data can save you a lot of time, and it can save you a lot of steps in sort of writing your code. Once you've got it into a tidy data frame, then you can sort of apply similar code from a different project to your new data frame. And using sort of this common sort of tidy data frame framework will reduce this kind of risk of making errors, because you're going to each time using sort of a common sort of step work and consistent package to consistent steps in your analysis, making it easier to extend. So at the core of tidying data, I think it's really rearranging the data and getting data into this tidy format where each column is based on a single variable. So sort of probably the most intuitive way to do that in R is using this tidyr package that comes as part of the tidyverse. And within that, there's two main functions, one called pivot longer and one called pivot wider. And the idea of pivot longer is that you could take a data frame like this, where you have a variable spread across columns. So these are all the same variable, but it's in two different columns, and that you can put it to a kind of long format where you have a separate column for year, right, which is itself as a variable, but it's really hidden in the column names in the original data set. And you have a separate variable for, in this case, cases, right? So the values here. So we can sort of get this type of output by applying this pivot longer to a data frame. So in here, this data frame is called table 4a. And then we have to specify the columns that we want to sort of stack on top of each other, that we want to rearrange. So in this case, it's the column 1999 and the column 2000. So in the second argument, after the data, we tell it which columns we want to sort of stack to make longer, to rearrange. And then the next two arguments are going to be sort of names that we create ourselves, that we tell pivot longer that we want to label for the two new columns that are going to occur. So because we're stacking, well, the names two, the first of this, is based on a description of the existing column names in the original data set. So here we can look at that and say, okay, these are years, so we're going to call it year. And this is what's going to appear as the title for the new column here, year. You see, look at that data frame. There's nothing to tell us that that's years. We have to tell it when we rearrange the data set itself. Okay, and the second one is for the values. So this right here in the yellow, right? These are all the values. And again, we don't really know what these are. So we have to tell R, these are cases. So this is what we're going to label it cases, or we could say population, or if it's fertility rate, we could say TFR or something. We can decide ourselves. So pivot longer is like super useful and quite I think now, like the languages is quite intuitive on how it works. It's just remembering that you need to first define which columns you want to stack on top of each other and what the names of the columns were to create this new variable that's like this kind of key variable, and then the values, a name for the values for the stacked data that's going to be created. Okay, so pivot longer, we use, I would say I use probably 90% of the time when I have to pivot a data set. Maybe 10% of the time I might be making it wider. Maybe less than that, maybe 5%. So in the case for pivot wider, it's the kind of doing the opposite manipulation. You see in this original data frame, we have a type variable where it's it's not really strictly a variable, right? It's a mixture of variable names. And in this count, it's certainly not a variable. We have different types of data in here in each cell. So the odd cells are cases, and the even cells populations. So we need to pivot this data wider. And in this case, we don't have a columns argument like we have for pivot longer, because we just need to define where the column names are stored, which is in the type column. So this is where the column names are going to that appear in the new data frame are going to come from, and the values where they're going to come from, which column are they going to come from. So in this case, it's label count. Yeah. So in this case, we're going to lose this count title. It's a bit vague as it is, and so these values are going to be separated depending on the column names that are stored in the type column. So this is just repeating what I've gone through before. I think the pivot longer sort of make sure data set are sort of stacked on top of each other, and we need to define these four main arguments. To demonstrate another example, we're going to use this TFR data from the United Nations. So this is the country names, the country codes, and with the UN data, they go across time, different periods, and then we've got the TFRs for these different country names or regions across time. So you can see this really should be longer, right? If we want to do anything in R with it, we're going to need to, like a ggplot, we're going to need to have TFR in a column and period in a column. So in this case, we can use pivot longer, where we take the data frame on the previous slide, and we're going to say from columns 3 to 16. So you see before in the example, we gave the name of the columns. In this case, we can also give the index of the columns instead. So here we're saying from the 3rd column to the 16th column. So I know there's 16 columns because it tells me the dimensions there. Okay, so I'm going to go from the 3rd to the 16th column. I'm going to stack on top of each other. So it's going to be what's 14 stackings are going on. Okay, and then the period is the title of the column that's going to be created for the key variable, which is a description of the column names in the original data set. And TFR is what the values are in the data set, right? It's describing this kind of yellow part of the data frame. If we think about back here, right, this is the TFR values, and these are the periods. Okay, and then we get a nice data frame here that we can then go ahead and plot or run a regression model on, or do many different types of things. So this next slide is just showing you an example of how we can select the columns in different ways. So we've already seen that we could write the names of the columns. We could write the numbers of the columns like we do here, 3 to 16. We could also write a range of the columns by their names. So here we say the 1950 to 1955 columns, then a colon up to the 2015-2020, which is the 16th column. We can write it like this. Or we could write any column that contains a dash in it. So if we look at the original data frame, these two columns we don't need to stack, right? They're different types of data. They're not TFR data in here. But any column with a dash in, we need to stack. Where are we? Yeah. And there's another way to go about it. So these are all going to produce the same data set, right? As we had before, is to select everything apart from the 1st and 2nd column. So we just put minus and then 1 and 2 for the 1st and 2nd column. These are the ones we don't want to stack, so we use the minus, and again, it's going to produce the same tidy data frame as we have here. And another alternative is the minus the name to the code column. So again, these are all just different ways to select the columns that we want to get. This is just describing probably what I already talked about, that pivot wider is doing the opposite from pivot longer, basically. Yeah, and we have the three arguments for pivot wider. So one example of when you might use pivot wider, I mean, it's very unusual to find data that needs to be pivoted wider, but sometimes I have used it in when I'm creating like a table. So in this case, imagine that we have this data set DF3, which is all the observations of TFR below 1.2 from the UN. So there's only about 17 observations here. And perhaps I want to create a table like this, right, just to show where they occurred at what time period. So in this case, I can pivot this data to wider by telling it that the column names are going to kind of come from period, and the value names are going to come from the TFR column. So period and TFR, and then it creates this kind of table, and it will fill in NAs where there is no observations there. So we can sort of get a little summary table of the observations. Okay, so I would really recommend going through exercise 1 to get used to pivot wider, especially. I think most of us, I think all the questions about pivot wider. It's really yeah, it takes a bit of time to get used to, but once you kind of get it, you feel quite like powerful that you can start rearranging data very quickly. And once you get the idea of these two ideas about well, selecting the columns and then naming the columns and naming the values, then you can really manipulate lots of different types of data. Okay. Also in the tidyr package, some other functions that can help with manage or sort of wrangling your data, let's say. So another two are separate and unite. And these are kind of, again, like pivot wider and pivot longer, kind of working in pairs. So separate allows you to sort of take a column that's maybe you can see contains multiple types of data in a single cell, and allows you to split it up. So maybe it's not super clear. Yeah, I'm zooming in, okay? So in this rate column, we have actually two values, but it's sort of seeing it as a bit of text, which is like 0.7k/19 million. So when we use the separate function, it can separate out these into two separate columns. So we give it separate the data that we're going to separate. So in this case, the object's called data3. Then the column that we want to separate. So this is the rate column, right? We want to separate it. And then we give the new column names that we want to separate it to. So then it separates based on it. What it essentially looks for anything that's not a number or a letter, and it creates the separation based on any sort of kind of punctuation mark or space. I'll go into a bit more detail about that later. So the unite is what am I doing? Okay, okay, unite is opposite from separate, right? So here we've got two columns, and we just want to squish them together into a single year column. So we can just do unite, the name of the data frame, then the two columns that we want to unite, and then the column argument is going to be the title of the new name. And if we want to separate it by anything in between. So here we just open and close the quotation marks that there's nothing to separate for. Okay, the final function in this slide is for separate rows. In this case, we take the data frame that we had before on the left here for separate, but rather than create separate columns for each, we might want to create separate rows for each. So in this case, we use the separate rows and we give it the column that we want. So this actually creates a longer data set, twice as long, because in each cell here, there's 2 bits of data. So it sees it and it creates a separate rows data set. So just to go into a bit more detail about separate, in this case, we're going to work with this DF2 data. Let's go back to it. Oh, where was it? Right there. Oh, okay. We're going to use this data, and we're going to practice separate on the period column here. Yeah. So let's go back to this. Where were we? Okay. So here we've got the DF2 data that I just showed you. I'm going to separate the period column. I'm going to separate it into year 0 and year 5, like 5 years later. And we're going to separate it. Here we can specify precisely what character we want to create the separation on. So here we're going to say we're going to do it on the dash character. So by default, we don't actually need to do that. But here I'm just showing you how we can specify the character on which the separation will occur. Okay. So, okay, let's maybe go back here just a note. what's being created is these two new columns. And these, you see, we get the CHR. This means it's a character string, right? It's not a number. So if we want to convert these to numbers, then in separate, there's an option to do that, right? So we can use this convert is equal to true, and then it will look at what's been created in this column, and it will decide if it can convert that into a number. And if it can, like if it just contains digits, then it will convert it into a number. So you see now they're integers, no longer characters, which means when we come to model or plot that it's sort of in the right format. Okay, if we want to keep the original column in there as well, we don't have to lose it. So we can set remove is equal to false. So again, by default, that's true and it drops, but we can keep it there with remove equals false. Okay, and this is just going into details, but this is what the default for the separation is. And essentially, this is sort of a, how do you call this? A regular expression to say that you will search in the column for anything that's not alphanumeric, right? Anything that's not A to Z or big A to Z or 0 to 9. So anytime it sees a star or a dash or a space or a dot or comma or underscore or any sort of type of thing, any type of character that's not in these ranges, it will create a separation for us. It will create that will be where it decides to create the split. Okay, and finally, a few other kind of useful functions in tidyr, maybe less rarely used, I would say. So these are sort of called expand and complete, and these help you to sort of quickly create tables or data frames given different combinations of values. Imagine we've got this data frame that we just created from a tibble. Okay, and what if we want to create something that's got all the combinations of the countries and the years? Then we can use expand and tell it we want to expand the years and expand the country codes, and then it gives us 9 rows based on the 3x3 combinations of the countries and years. A complete allows us to go even further, where we can define for the year a kind of a sequence, right? So we have the years back in the original data going from 2010, 2020, 2015. But say we can here, we're saying we want years to be a full sequence, given the range of the years that are there and going in steps of 5. And then this creates the an even larger data set, given the complete combinations, given the year definition. Okay, and finally for tidyr, the missing values, how to handle missing values. So if we want to drop missing values, any rows with missing values or rows from where a particular column has missing values, then we can use the drop NA function. So here we give it the data set that's called X, and we're saying in column X2, when there's an NA, we want to drop those rows. So it sort of shrinks the data set down to the rows where X2 is not NA. If we want to fill these values up, and replace them with a value, we can use the fill function. And what this does is sort of scrolls down and takes the value above to fill it up. And so you see this one's filled with 1 and 1 because it's taken 1 from above, but then we get an observation. So then the next missing value is filled from the one above. And by default, this has a direction called down up, right? So that means it's going down, down, and down. But for example, if there was a missing value in A, there was 1, there was NA, but B was 1, then once it's gone down, it will go back up and sort of drag the one up there. And finally, for missing values, this replace NA. This allows you to specify a single value for all the missing values in a particular column. So in this case, we use replace NA. The data frame is called X, right? And we create a list where we're saying the variable name and the value to replace the missing values in that variable. So here we're going to replace all the missing values in the variable X2 with the value 2. Okay, so it's just a summary of what's going on in each of these tidyr functions. And then the exercise to practice mainly the separate and the pivot wider, the separate and the separate rows and the drop NA functions. So again, this will probably take, I think maybe it takes 30-40 minutes in the classroom. Okay, so that was the tidyr package, right, for tidying up the data to try and get it into tidy form. Usually, that's not where we want to stop when we come to data analysis. So usually we might want to sort of filter the data or rearrange the data a little bit to get certain columns in a different order. or even rows in a different order. Or maybe we want to join together data frames. And so for these kind of operations, there's a package called dplyr, which I'm saying it's become very popular way to do data manipulations in R. So it's pretty fast. There are some faster packages when you're dealing with massive data frames, but I mean, most of the data I deal with might go to a few million rows, and I barely have to wait only a few seconds to do most data manipulations, and I tend to use dplyr a lot. So dplyr comes from plyr, which was named after like pliers, like this sort of tool that you might use to change things around. And plyr was based on different types of data frames and being applied to that. But dplyr is just for data frames. So plyr used to work for arrays and matrices and lists, and it was very general. But dplyr is just for data. So within dplyr, there are 6 functions that do pretty much most data manipulations that you might want to do once the data is in a tidy format. So we'll go through each of these in the rest of the slides. There'll be some join functions at the end. So the first is select, where you're really working on selecting variables by the name. Filter is where you're really picking observations, going sort of row-wise, and arrange is sort of arranging the rows in a particular order. Mutate is for creating new variables or overriding existing variables. And summarize is when you want to collapse down the data to create some sort of summary variables. So all of these, in particular mutate and summarize, can be used in conjunction with group by, which is like the 6th function that I didn't mention yet. And group by allows you to create manipulations by a categorical variable in the data. So maybe you want a grouping summary, you want to summarize by group, or maybe you want to create a new variable that has a grouping summary to it. So in this case, you can use group by in combination with these, which we will go through how to do. So the nice thing about all these functions compared to like alternative versions in like a base R is that they all work very similarly. The first argument in the function is always the data frame, and then arguments after that are always describing what we're going to do with that data frame given the function that we're using. So the other nice thing is that we no longer sort of need to define in each function the put like the data name and then $, and then the column name. So because their first argument is the data name, we don't need to keep writing the data name, which I'll show you a little some examples of older code where we would need to do that. And everything that we every sort of manipulation will lead to a new data frame, a sort of manipulated version of the data frame. So they will output that. Okay, so the select function can be used to collect subsets of variables or columns of the data set. So this works by just writing select, the name of the data frame, and then the columns in the order that you want them. So remember here there's a country code column, but we've not selected it, so it's been got rid of. And just like we used for pivot longer, we can use these different ways of indexing to select the columns. So we could use, rather than the names, right, we could write column 1, 3, and 4, or we can use -2 to get rid of the second column, or we can use these helper functions. So we saw contains before, or starts with, or matches. We can sort of use these. So here's just some examples of selecting the same data frame. So all these will give the same output, right? All of these are taking the data frame df2. We can select the name, then the period to the TFR column, or we can take the first, third, and fourth column, or minus the second column, or minus any column that starts with C, or minus any column that contains the letter C, or just minus the code column, right? They all would give us the same result, just different ways of selecting the data frame. So it's a very flexible language in dplyr to work with. So that was selecting columns. If we want to think about extracting cases, then filter is sort of the main function that we would use to return rows that match a given true or false statement. It's also the distinct function, which is very useful. It just removes any duplicate values. So here we see that there's 2 green lines, right? So it gets rid of the green lines, and there's 2 gray lines, so it gets rid of the light gray. Slice allows you to kind of look up a particular row. So you would slice the data and then the row number that you want. And top n returns like the first n observation. So it's a bit similar to add. Maybe it's a bit easier to explain with an example. Okay, so first filter. So filter, we have to give a logical argument. So remember right back to the second set of slides when we talked about the true or false and how we can do that with the less than or greater than. Or in this case, we're going to use the equal. So we use two equal signs to say what we're searching for a match when period is equal to 2010, 2015. And then it will give us the results for all countries if we just stop there for 2010, 2015. But if we want the China data as well, then we can put a comma and the name is equal to China. And we just get the one row out of the a few hundred that's in the data. Okay, so here I just wrote in the comments, right? Remember, we could use double equals or less than equals or not equal. And another useful function for this is the in function. So we see this down here. So in this case, okay, I've just done a filter based on China and when the TFR is less than 2 to get a subset. And in this case, when we want multiple matches, so rather than here, we're just, each time we're matching based on one thing on the right-hand side. But if we want multiple matches on the right-hand side, then we can use in. So here I'm looking for when the code is in this set of codes. So this is the code for China and Korea, right? And so we get that data based on the code filter and the period filter for these last two observations. Okay, so the next part, before we go any further, is probably to going through the deep IR verbs, is to mention this pipeline operator. So this is becoming very popular in R, I would say. People are already using it because it allows you to really write very nice R code and to sort of tie it together in a logical order. So this operator we see a lot. Yeah, like I say, it can tie together your R commands and it avoids you nesting code. I'll explain that a little bit later. And the syntax that we get, so the actual code as we read it, is a lot easier to write and explain when you use this type of pipe operator. So what the pipe operator does, it takes whatever is before you've written the pipe operator and it drops it in as the first argument for the next function. So if we do x pipe mean, that's the same as writing mean x. Okay, there's not a big advantage. Why would you want to do x pipe mean? But the real advantage of this pipe operators is when you want to do a sequence of operations, manipulations. So in this case, we've taken x, then we've logged it, then we square rooted it, and then we've taken the mean. So we've sort of chained together the different sequence of operations into one line of code. And this means, especially when you come to data frame manipulations, often you want to do more than just a filter or select, and you want to do multiple operations at the same time, then the pipeline operator becomes very useful. So like I was saying, it allows you to easily build up a readable code. It's good practice to start a new line after each pipe. So here I'm using the pipe, I start a new line, then I use the pipe, then I start a new line. And when we do that in our studio, it automatically creates this indent, which again, makes it a bit easier to read. And so I guess the key to the pipeline operator, at least for me, to understand it, was thinking whenever you see that, the pipe written, is to think in your head, that means then. And so read it as the English word then. So this allows you to sort of read the code a bit better, right? So you can think of this as we take TF2, then we filter it to the China data, the TFR less than 2, and then we take the tail of the data set for the last 5 observations, right? So this is fairly becoming a bit more like English, right, to read. Whereas if we didn't use the pipeline operator and we wanted to do that type of data manipulation, we would have to kind of write it like this with the nested parentheses, right? So we take the tail, sorry, I skipped ahead, crazy man. Okay, so we take the tail of the filtered data frame at China. I mean, this is, you have to be very careful when you're writing this, that you're opening and closing brackets, right? But this, you can hopefully see it flows a bit better to think about it. Okay, so as I said before, you've got to think that this pipeline operator means we take whatever's before it, which is df2 in this case, it goes into the first argument, which is the data argument here. And then again, we've got the pipeline operator. So whatever's before it, which is in this case the filtered data frame, is going in here before the n is equal to 5 is the filtered data frame. So it takes everything before and filters it. So along with the pipeline operator, sometimes, but not a lot, but sometimes you need to use this dot which is called a placeholder. So it represents the results from everything above higher up in the code chain, but allows us to put us somewhere else in the function. So remember, everything before was going into the first argument, but perhaps the function you want to put everything before as it goes into the second argument. So in this case, for example, we've taken the data frame, and then we want to feed the data frame into a regression model. So for LM, the regression model, linear model in R, the formula is the first argument. So we don't want to put the data into the formula argument. We want to put it into the second argument, the data argument. So that's the placeholder can help us do that. So what I'm saying, it's useful if you want to pass the results from everything higher up there in the code into an argument that is not by default the first in the function. So in most cases with tidyverse functions, it's not really a concern because the data is usually always the first function. Okay, here's just an example of what I was showing in the other code, right? That we could take the DF2 data, we filter it, and then we put that data into a linear regression model where we regress the TFR and the laggard TFR, and we get the results out. And another example of the pipeline operator and the placeholder. We take DF2, filter the China data, put it into the regression model, get the residuals, and calculate the standard deviation of the residuals. So you can really see the use of the placeholder and the use of the pipelines to create a kind of readable bit of code to get the operations. This is what exercise 3 is about. It's really practicing with the pipeline operator and also practicing with filter and select. So I would say this is again like another half hour to go through this exercise properly and to get used to using the pipeline operators. Okay, so the next part is on creating data. So if we want to create a new variable using dplyr, the way we do that is usually using the mutate function. So this allows us to either overwrite an existing variable, or we can create a new variable itself. Then there's some other variations on it. So mutate at, mutate if, and mutate all. They allow us to do create multiple columns at the same time. And transmutate, I probably never use. It just gives you a single column at the end. And rename is just for renaming columns. So a few examples of these. So here I'm taking the DF2, then I'm mutating it, and the TFR data, I'm replacing that column with a rounded version of the TFR column, where it's rounded to one decimal place. And then I put a comma and start a new line saying I want to create a new variable called location type here, where I'm going to use an if-else to create a categorical variable. And if the code is greater than or equal to 900, then I'm going to say it's a region. And if it's less than 900, it's equal to a nation. And see what comes out is a table that's 3,000 long, 3,100 rows long, just like before. But the TFR is now rounded to one decimal place from this overwriting of the original TFR. And now this location type is now a new column, a fifth column, based on the code. So here the code is greater than 900, so it's region here. Let's just go back to the original DF2. Yeah, well, we can see DF2 here, okay? We've got the TFRs to more than one decimal place. But when we've done this mutate, then it's been rounded to one decimal place. So it's sort of overwritten. So when you're creating new variables, and if you want to create a categorical variable that has more than two categories, then if else can get tricky, right? Because you can only get a yes and no answer from that. So case when is like a kind of more general version of if else that allows you to create multiple categories. And so here's an example of it in action, where we create a new column called location type again, and then we're going to define how we create the categories. So in this case, if the code is less than 900, we call it country. If the code is anywhere between the first 6 code in the data frame, then it's an area. And then for the remaining codes more than 900, we call it a region. Maybe this is not the best illustration. Yeah, well, we can see there's a location type column, a new one here, where we've got the area in here rather than a region. But yeah, we can also filter further down where we see country and region for the different codes. Okay, and then a recode function again allows us to create a new function where we take the variable name that we want to recode, and then just like we saw with recode factor, on the left-hand side we put the original label. So remember before we got Africa, and we're going to recode that to continent : Africa, and further down in the data frame we might do Eastern Africa as region : Africa, right? So then this goes through the name column and recodes the categories according to the pattern that you've styled here. Okay, and finally, one more sort of useful function to work with mutate is cut. So the cut function will divide a continuous variable into categories. So in this case, I've filtered the data just to the country data and the last period. I've selected or unselected the code in the period column. And I've created, so this is what's left, the country and the TFR. And then I'm going to create two extra variables in the mutate. One called interval 4, where there's 4 categories, and one called interval 7, where there's 7 categories. And both of them are based on the cut function on the TFR variable. And in the first one, in the TFR interval 4, I create 4 breaks, right? So there's going to be a range for the first kind of window, which is between the minimum TFR and 2, then 2 to 4, then 4 to 6, and then the fourth one is 6 to the maximum TFR. And then it creates this kind of a category. You see it's a factor variable for the category that each of the TFRs fall into. So for example, Mauritius goes from the minimum TFR in the whole data, which is 1.1, and 2. So there's 1.39 lies in this interval. So TFR interval 7 is similar, but we've created 7 intervals going in steps of 1 from 0 to 7. So you see these interval labels are just between the integers, and they're putting the TFR in the correct place. Okay, so that was mutate, and then we also mentioned rename. So this is when we want to rename a column. So in this case, we've taken the TFR column, and then we're renaming it as fertility rate. So we've got the old name on the right, the new name on the left, and then we see get this new column name here for fertility rate. And if we don't want to write the old name out, we can just write the column number, the index of the column number. So here we're just changing the second column, which is code, and we're changing it to country code to get change the column name on the second column. Okay, and then just some examples with these multiple mutates. So if we want to mutate multiple columns, then we can use a true or false statement for each column. So if the column is numeric, so in this case, the code is numeric and the TFR is numeric, then we can multiply the number. The mutation we want to do is multiply the number by 100. So the TFR increases by 100 and the code increases by 100. And mutate all is when we want to just mutate all the columns that we have left in our data frame. And again, we use this sort of tilde sign to say we want to create an operation, and then the dot is like a placeholder. That's the value that are going in, and then afterwards is the operation that we want to take place. Okay, so the next function is the arrange function, which has unsurprisingly arranges the data according to the value of the column that you specify. Yeah, so here we're going to arrange the data for China according to the value of the TFR, and then it goes from the lowest to the highest TFR. If we wanted to go the other way around, we can use the descending function, DESC, and then it will descend from the highest to the lowest function. So again, we use the arrange function there. Okay, so arranging, well, factors, knowing about factors that we talked about in the last set of slides can be useful when arranging the data. So here I read in, okay, maybe this data frame looks a bit, this code looks a bit complicated, but perhaps we can understand it, right? I read in the UN data from this Excel sheet. I've skipped the first 16 columns, and I've, whenever I've seen this symbol, I put it to an NA. Then I've selected the 3rd, 5th, and 8th column, and any column that contains a dash, and any column that contains a plus. Then I renamed the first, the second, and the third column to name, code, and year, and then I pivoted longer. And this creates this data frame, right, for us. And we can sort of see how a range is going to work. So if we look at the age group, the ages, at least they appear in order here, but we can see it's a character string. So this means when we arrange it by age group, it goes in sort of alphanumeric order, right? So anything that starts with a 0 is seen as the first age group. Anything that starts with 1 is seen as the second, and 100. So we kind of get this funny order, right? Because it's arranging kind of alphanumerically. And that's because it's a character string. So this is, as I mentioned, when we use factors instead of character strings, it allows us to define the order for categorical variables. So this is what we do in this, this bit of code here. We take the data set that we had, and we're going to update or mutate the age group variable, and we're going to put the factor, we're going to create a factor, and it's going to be in the order that they appear in the data. And then when we do the arrange, we get it in the order that we would expect when we arrange by the age group. Remember before, when we arranged by the age group, we got it in this funny order because it was going sort of alphanumerically. Okay, so exercise 4, I think it's lots of practice with mutate mainly, and some arrange, and case when and if else. So just creating variables, and again, that would take longer, maybe 40 to 50 minutes to go through this exercise and get some practice on handling data and mutations. Okay, so towards the final parts of dplyr code is the idea of group data. And group data allows us to sort of add some characteristics to the data, which then we can do some manipulations with. So we sort of change the unit of analysis from a complete data set into groups. So this images is quite useful, right? If you imagine we have a data frame, and like the last column here is a grouping variable, right? A categorical variable. Then when we use group by on that data frame, it essentially tells it to split the data frame up into the groups that we have it. It's still like one data frame, but it just says there's this variable there that we want to sort of group the data by. And so we can do that using group by. And that allows us then to sort of summarize the data by each group, or even add columns with new summary variables in them. So maybe well, before we get to that, let's talk about summarize. So summarize allows us to sort of summarize the data frame, either the whole data frame or by group. And usually when we write summarize, we would write the new column name that's for the summary data set, and then a function that we're going to apply to create the summary measure. So we can use n, which is going to tell us like how many rows there are in each group, or n distinct, telling us how many distinct rows there are in each group, or values in each group. Sum is going to tell us like the sum of the values, or the mean and the median, like these ones that we covered earlier, or the first or the last, for example. So it's a bit easier to see with an example. So here we have the data frame again from the UN, the age structured data for all countries. So you see there's 80,000 rows in here. Okay, so we're going to filter to the 2015 data and just for China and Japan, and then we're going to summarize it. So when we summarize it, we give a new column name that's summarizing the data, and then the function that we want to apply to summarize it. So here we're going to summarize the population column, and we're going to summarize it using the sum function. So we're adding up the populations in China and Japan in 2015. So what we get out is a data frame just with one row and one column, with the pop sum based on what we wrote here, and the value based on the operation on this data set, on the filtered data set for 2015 in China and Japan. Okay, we can use summarize in combination with group by, like we talked about before. So in this case, I'm going to do the same filtering, I'm going to drop the missing values, and then group by the name column. So remember, there's 2 countries left in here, China and Japan. And then for each group, I'm going to create 3 summary variables, right? One called pop sum, which is the same as before, where I've just summed the pop. N is going to tell me how many rows there are in the original data, and under 5 is going to tell us the first population, so the population in the first group. Remember, this is age structured groups, right? So it's going to be the under 5 population, because that's the one that appears first. So what we get at is this, we get a little printout telling us what's happening, and then it tells us we're going to get 2 rows because we've summed by, we've grouped by name, sorry, and there's only 2 countries left in this data set. And then we get the 3 extra columns, summary columns that we create here using these data manipulations. Okay, so just another example where here we filtered to any country where the code is less than 900. So this is basically all the countries in the UN data, none of the regions. Then we group by the name and the year. And then we've created a pop sum column again, where we've summed the population and removed any missing values from the sum calculation. So here we get, remember, if we go back, there were, 80,000 rows? And this was age structured data, age and year. And now we're left with just the country and the year. So we've lost age. We've summed over age. We haven't really lost it. We've summed over it. So now we get the population sum in each year. These are in thousands, right? So telling us we got 201 groups. So these are the 201 countries in the UN data. And then for each of them, we've got, what have we got? 15 odd observations, maybe 16, for each year. Okay. So just a final example on group by with mutate. So far we've been doing group by, then summarize, and now we do group by mutate and see the difference. So here we take a data set, again the TFR data set this time, with 3,000 rows. And then we're going to filter to the China and Japan data again, and we're going to group by each country. And then rather than summarize, we're going to do mutate. So remember, summarize sort of shrunk the data down where each group was leading to the rows. And mutate sort of avoids that and just keeps still keeps the grouping sort of characteristic to it, but it no longer squishes the data down to summarize by each group. You just add extra columns and it will repeat values if needed. So in this mutate, we work out the mean TFR for each group, right? So to do that, we just use the mean function on the TFR column. And you can see here, we got the mean TFR. So for China, it's all the same value in each year, right? It's just taking the mean TFR by looking through the time for China. And for the maximum TFR, again, it's the same, right? It's the same value because it's just basically look through this data, found the maximum value, and then repeated it here. So if we were doing a summarize, it would just be one row, right, for China, and then the TFR and the mean TFR. But here we've sort of kept it in, maybe as some kind of summary variable. And then lag TFR essentially goes through each of the rows and then lags the value by one period, okay? So you see the TFR in 1950-55 was 6.11. So in 1955, 1960, the lag TFR is this 6.11. So it's basically taken this column and shifted it down one. This is what the lag function does. Okay, so the exercise 5 is just practice with group by. So it does take definitely some practice and getting used to creating summary variables, but it's a very, very powerful tool to create many different types of summary data frames, and it works very fast for most combinations of data. Okay, so the last bit on this slide is on relational data. So this is really bringing data together based on some common column or row. So like I say here, data analysis really involves just using a single data frame. Usually we have to combine data to answer the type of research question that we're interested in. And we can think about this combining data in two ways. One is joining variables by columns, which we'll deal with later. And we'll start off with the simpler case where we join data by different observations by rows. So to join by rows, we can use this bind rows function. And this is kind of an example here where we have a data frame called X and a data frame called Z. And then we can bind the rows. So we can do bind rows X and Z. And then we get out sort of a new data frame that's got the two joined together. So these three other functions are kind of not so, I mean, I don't use them a lot, but sometimes I could use them. And this is essentially looking row-wise for the intersection. So looking for the common row in both data sets, you can use intersect. For the difference in the two data sets, you can use set difference. And for the union, so it's sort of filtering out the duplicate values, you can use the union. These three I rarely use. I mean, I don't use bind rows that much, but even these three are even rarer. So just an example of bind rows in action anyway. So here we've got two data sets, much like in the diagrams before. And here I'm going to sort of show you the R code where we bind this data set D1 to this data set D2. And then you see what happens is we get this final data set out with six rows. We've had 3 in each. And in rows A and B, they've sort of stacked on top of each other because they both have these common column names called A and B. But in D1, we have a column C, whereas in D2, we have a column D. So when we bind the rows, we're unable to give values for what's in column C on the later rows, and the same for column D when we add this. So bind rows will create these NAs to fill in the missing places. So here's just another example where we have the common column names. In this case, we don't get any NAs because there's no column that is unique to a particular data set. So exercise 6 is quite a quick one, just reading in different data sets from different sheets in a UN Excel spreadsheet on population by age, and then just binding the sheets together. So there's like one sheet on the past data, and then the other sheets, I think there's about 10 sheets in that Excel spreadsheet that are on different scenario projections of populations. So we can sort of stack them together and create one big data frame using bind rows. Okay, so that's all about combining sort of row-wise, and then the last bit we'll talk about combining column-wise. So there's an equivalent to bind rows, which is bind columns, and this is like very simple way to sort of squish two data sets together. And yeah, I could say, yeah, I don't use it too much, and it's quite dangerous to do. You sort of have to assume that the observations in the rows are in the same order, and that it makes sense to sort of put them together. And that rarely happens unless you're really using the same data supplier for all your data, that the observations are in exactly the same order. So more common is to use this function, joining function. And in particular, left join is the one that I use probably 90% of the time again. So in this case, when we're combining variables, when we're combining data sets, sort of column-wise, we will add a new column onto the data frame from another data frame. We need to identify one or more columns that are kind of key in joining them together. They're sort of common in both, and allowing you to do the sort of linkages between the two data sets. So in this case, we have a data frame X and a data frame Y, and they have column names ABC and ABD, right? So when we do left join, essentially it's going to use the common column names A and B to help us add on this column D to the left-hand side. Remember, X is on the left, right, and Y is on the right. So D is going to be added onto the left-hand side. So it basically goes through each row by row, and it sees that A and B here is A and T, so it's going to add on this 3. Then in the next row, it's got B and U, and it finds the B and U and adds the 2. And then it's got a C and V, so it looks for a C and V, but there's no C and V here, so it gives us an NA. Yeah. So by default, it's doing this join by joining on the A and B columns. But we can explicitly state how we want to do the join by using the by argument, and or we can either, and if we have the different column names, then we can write it as a kind of vector format. Maybe that's a bit clearer in the next few slides. Here I just got a nice animation again, sort of showing you how it happens when you've got multiple joins. Okay, so we started off with the 2 different data frames, and then it for this observation 2, it sees that there's 2 possible ways to 2 values of 2 on the right hand side. So then it creates an extra value, so it doesn't lose this Y2 and Y5. It just repeats the X2 on the left and then adds on the Y2 and Y5 from the right. Okay, with the 1, it sees the X1, so it adds that to the Y1 matches. And for the 3, it sees it's got the X3, but there's no 3 in here. There is a 4, so it's going to drop the 4 and get rid of that. So maybe I can sort of go through these ideas a bit better. in the R code in the slides. So here we have the D1 and the D2, just two data frames kind of match what we did before. And then you can see the join happening when we do left join D1. So that's on the left, and we're going to join the D2. And you see it prints out joining by A and B. So we sort of know what's going on when we do left join. In this case, the second case, we are getting the same result, but we are explicitly stating, using the by argument, how the join is working. So we're saying column A on the left is going to be joined to column A on the right. Column B on the left is going to be joined by column B on the right. And we get the same result. So it's useful to have this kind of functionality when the names are different, right? And we still want to do the join. So here in D1, we have the same data set with ABC. But now in D4, we have a data set AA with column names AA and BB and D. So in this case, column A on the left is going to equal to 2 A's on the right on this D4. And column B on the left is equal to 2 B's on the right. Remember, we've got left and right here, D1 and D4. And then we get this, the resulting data frame. Okay, and this is just a bit about the multiple matches that we saw in the animation. So multiple matches, well, when one table has duplicate observations in the key variable, kind of the variable that we're matching on, then multiple matches will increase the number of rows in the outputted data frame. So this might not always be the intention, and it can happen. It can happen that you do a left join and somehow your sort of data frame mysteriously grows and you're not quite sure why. And it's usually because there's multiple matches, and perhaps there's some duplicate values in one of the data frames that you're joining on. So it's just an example of it again, where we've got D1 as before, but now we've got a new data frame D5, and we've got these columns, rows A. And then we've got 3 values of C that are going to match these values of C here. So when we do D1, left join D5, we're going to join by A this time. Yep, and then we're going to get the A and B, the rows before, where we found a match for A, but no match for B in the second row. And then for column C, then it's kind of dropped off a bit, but we can see for column C, we got the C, V, and 3 in A, B, and C. And then the column of D goes 3, 2, and 1 is missing just off the slide. Okay, so that hopefully gives you an idea of how to do joining. So we've got the left join function. There's other join functions that I really don't use too much, but they're just there for completeness. I think right join is kind of the opposite of left join, just going in a different direction. Inner join can be useful to filter out. It just takes the complete cases, a bit like the intersect in the previous rows case. And full join as well can be useful actually when you sort of create these extra NAs where there's no matches on either side, so you don't lose all the data on the right. And exercise 7 there is just practice with the joins, I would say. Yeah, so it's mostly left join, like I said, is what I use most of the time. I think most people using it focus on left join. So again, that's a shorter exercise, maybe 20-25 minutes to do this exercise. And then we've got the cheat sheet as well, which is in the handout as well, talking about different ways to tidy the data, reshape the data that we've gone through. I should mention gather and spread were the old names for pivot wider and pivot longer. So they updated it maybe a year ago. These ones are a little bit difficult to really follow, but they're very similar to pivot longer and pivot wider. So sometimes if you're looking online, you might see gather and spread, but I think nowadays trying to phase out gather and spread and tidy off for pivot wider and pivot longer. And on the back, on the dplyr spreadsheet, we've got all these different ideas of summarizing and mutating and filtering and arranging. And then we've got the different summary functions and the different joins and row joins and column joins. Okay, so maybe we take a break there and then for 10 minutes, and then we come back for the smaller, shorter set of summary slides at the end. So maybe 10 minutes. Okay.